Oh, yeah.
So what we're going to do is we are going to simulate an AR model, an AR1 model, and try to estimate it, using what we've done so far. So length, we go for 1024. Object X, not damage. So that is an AR1 model.
So it's like a super erratic curve.
So as you can see, it's going back and forth. It just doesn't look like noise. Noise, if you look at it, centered around 0, and it will sort of have a band around it. So we can find the variance of the series. The variance X is 5.936939. The coefficients that I'm using is 0.9.
Okay, just double check. This is the one where you can, where it doesn't matter if the coefficient is positive or negative, right? As long as its absolute value is less than 1.
Yes.
I think it's in a different window.
Oh my God, that means sounds really good.
Where is it on?
I think it's in a different window.
Oh, it's still here. Thanks. I forgot to close it. So I did an Acf plot, and you look at this, and at 0, we've got 1. Typically, that's what we would expect, because the autocorrelation at 0 is 1. But it's going this way.
You said,
right?
you said typically, so there's like variations that it's not 1 at 0.
Yes, we're going to solve that. So it's decaying, and you can see we used an AR1 model, but if you look at it, about 15, 16, 17 of them are acceptable coefficients. They all lie outside the boundary. So the original model is AR1, and if you go with this, you're going to fit a model that is AR17. So you're having way too many coefficients that are unnecessary. So what went wrong, or what is happening? So an autocorrelation function plot is used to identify the order of a moving average model, not an autoregressive model. So to determine the order of an autoregressive model, we are going to use something called a partial autocorrelation plot. So if you look at the partial autocorrelation plot, at 0, we have nothing. This is why you said it. So what is partial autocorrelation? Suppose you have yt and you have all the way up to yt minus 3. So instead of looking at the correlation with every previous time point, we're going to assume that whatever that's in the middle is known, and we're simply going to find the correlation between yt and yt minus 3. That's the right way to do it. So in this case, at 1, I've got a peak, right? And everything else is 0. So that is an AR1 model. Yes? And you look at that, the very first peak is about 0.9.
So the last one was, so this is the AR1 model, and the last thing you showed us was just
MA17. Now, why does it happen? Why does an AR1 model show itself as an MA17 model?
Was it because of the coefficient that you picked? Like 0.9 would have been different if you picked like 0.3?
No. This goes back to last class, the task. Do you follow my question? Why did the AR1 model present itself as an MA17 model? There is a thing called invertibility. That's my hint.
It's called
Invertibility.
what? Okay, I just heard availability. I was like,
The,
wait.
um,
Do that.
the roof must lie outside the unit circle.
Sure.
So like all the MA17 values are in the unit circle.
No.
Yeah.
This has to be outside the unit circle. The root that you find. Now, if you divide by the characteristic polynomial, what can we do here? What did we do anytime we had 1 over the characteristic polynomial? This is phi of z. This is example 1. So what did we do with 1 over phi of z?
Found the roots.
I found the roots.
Or no way. Assign it to or
That's the H.
Even else, but I had said, well, instead of 1 minus the theta 1c, it's 1 plus theta 1c.
So I don't know what you're talking about, but
Like at the top where you have the,
For the characteristic polynomial.
for the polynomial, now you're looking at an MA model.
oh, that's just in general.
So I'm looking at an AR model. So we have 1 over phi of z, and we wrote it as psi of z epsilon z. Yes? We evaluated psi, which gave us a series. And that gave psi naught, psi 1, epsilon t minus 1, psi 2, epsilon t minus 2, dot dot dot. Correct? So what it's saying is up to all the way for t equals 17, these values are significant for this particular model.
Oh, that's an M.
Past 17, it becomes 0. So which is why the given AR1 model is or can be represented as an MA model. In general, any AR model can be represented as an MA infinity model, provided the roots are invertible. Provided the time series is invertible. It happens if the roots of the characteristic polynomial lie outside the unit circle. Does that make sense? So it is invertible on the AR side if the roots here lie outside the unit circle. It is causal on the MA side if the roots lie outside the unit circle.
Okay, so that on the board is an MA.
What? This is an AR one. So, good. So if I can invert on this side, if the roots lie outside the unit circle, that is the condition for invertibility. If I can invert on this side, roots lie outside the unit circle, then that is a condition for causality. Does that make sense? Causality, invertibility. So you look at that first value of the ACF. What do you think that corresponds to?
0.9.
0.9, the parameter in our model. So if I typed P, I get 0.887, right? So sure, I can't get the exact value because, you know, we're estimating, and that's a very good estimate. I get 0.887. So for an AR1 model, it is easy to estimate the parameter phi1. Good. And how do we estimate it? We estimate it by looking at the partial Acf Plot.
So first off, that's just the general, like, it might not match up exactly for our notes, because it's general.
It does match up to that, but it's way before MA model,
So
right? It's not on the MA model part. Remember when we did difference equations and had the characteristic polynomial on the left-hand side, right? And then we divided it, found the constant C1 lambda 1. All we are saying is we will be able to find these sideways using the expression that we found if the roots over here lie outside the circle. Then invertibility. If you can't invert, then you're able to find these side values, the sideways. Does that make sense?
okay, so this note is just way back, and that's why.
Yeah.
Okay. Also, so in this, if you had the coefficient is like 0.3, then the 0.3 would correspond to the 1 instead.
Why don't we try that? Yes. Now, if I reduce the sample size to say 100, what do you expect to happen with the estimator? Is it going to be better? Is it going to be worse?
So you lowered it, right?
Huh?
You lowered it.
I lowered it.
It'll be worse.
It's going to be worse. So I used 0.3, but the estimate is about 0.4. So, which makes perfect sense. The longer you observe a time series, the more accurate it is going to be for you to model the data. So, suppose if I had
So this time there is no.
another coefficient, 0.1, what were you saying?
So there isn't, so nothing equals 1 in that case.
What do you mean? The coefficient of this model that I had was 0.3. Phi1 was 0.3. So I estimated it to be 0.39. It's not close to 0.3 because the sample size is small. The length of the time series is not as large as it was before. And going back to 11th of 2024, now I have two coefficients, 0.3 and 0.1. And that's what I get. So still at 0.3, I get a value. 0.1, the next one is very borderline, right? So it could be significant. The rest went below.
Well, actually, a few of them are above and a bit.
Come again?
Some of them are above.
So once it drops down, that's it. Everything else doesn't matter. It can pop up again, nobody cares, right? Once it goes below that line, that's it. So maybe I'll increase the sample size to 2048. And you can see that the AR3 model, excuse me, AR2 model is right there. Good. In this case, we are able to look at the model and able to come up with values of the coefficients. But AR2, if it had complex roots, it's a characteristic polynomial has complex roots, you can't simply pick it out from partial autocorrelation from. So here we have 0.368 and 0.092. If I simulate a different one, I'll get 0.368, 0.092. Yes.
But even with the out of the AR model, when the H is 0, it'll always still be 1, right? Like the phi of H. Or am I thinking something completely
You're thinking of something completely different. So sometimes you may end up having coefficients that would make the series not stationary. So you've got to be careful with the coefficients that we have. So in this case, probably one of the roots or both of them did not lie outside the unit circle. So we require, if it's an AR2 model, both roots of the characteristic polynomial must lie outside the unit circle. That's a condition. Are we clear? So to identify the order of a moving average process, we use the Acf plot. To identify the order of an autoregressive process, we use a PACF plot. Do you understand? Okay, cool. Came to a conclusion that if we have yt equals 3,1 yt minus 1 plus epsilon t. Epsilon t is our standard Gaussian noise, then we can estimate phi1 using the partial autocorrelation function. And last time we determined that rho h was simply phi1 raised modulus of h, not modulus, absolute value of h, for all values of h, right? Greater than or equal to 1, 0 otherwise. So I can find the autocorrelation, and last time I showed that if the root is bigger than 1, then we will have inversibility. How do we get a root bigger than 1 if phi1 is between 0 and 1? Right? If phi1 is a fraction, when we move this to the other side, and we get a characteristic polynomial, find the root, that will lie outside the unit cell, and things would just work nicely.
I'm sorry, can you just repeat that?
If phi1 is between 0 and 1, and we move it to the other side, the characteristic polynomial will have roots that lie outside the unit cell.
Okay,
From last time.
yeah, that's where phi1 can't be bigger, greater than or equal. Okay.
Okay.
And if the absolute value of phi1, it can't be greater than 1, right? So greater than or equal to 1.
Come again?
If the absolute value of phi1, it can't be greater than or equal to 1, or
That's correct. So we move on to an AR2 model. So AR1 model will be the last topic for exam 2. And that will be during the first week of November, November 4th. AR2 model we have yt is equal to phi1 yt minus 1 plus phi2 yt minus 2 plus epsilon t by the present.
so just double checking. So when you were showing us the AR model on R, that when you were using like a 0.9 and a 0.3, that was the phi1, right?
Mm-hmm.
And that was why
Phi1 and phi2.
yeah, that was why it didn't equal 1 and equal to either 0.9 or close to 0.3.
Yes. So that is an AR2 model because we have two coefficients in the sense whatever that happens at time t depends on t minus 1 and t minus 2. So two-day regression. So we can write this as yt plus phi1 L yt plus phi2 L squared yt plus epsilon t. I'm moving all the terms to the other side except epsilon t, so that I can get the characteristic polynomial. What do I have in common? I have yt in common, so if I pull yt out, and that's what I would have. As always, if they lie outside the unit circle, make the real, make the imaginary, doesn't matter as long as it lies outside the unit circle. The AR2 model is inverted. So do make this correction. If we have yt equals theta of z epsilon t, and if the roots of lie outside the unit circle, sorry, I just put them backwards, then I did write this correctly the last time, right? Tuesday. Then the MA model is invertible. And what type of weights did we find when we inverted and put it on the other side? We gave it a name.
Casual. Wait, I'm sorry.
Casual.
I'm sorry. I said it's good. What was the question?
So on this side, we had sine weights. When I moved it to the other side, I used a different letter. Pi weights. So modulus invertible condition is if you sum I equals 1 to 0, the absolute value of pi I must be less than infinity. Well, that simply means pi I must be decreasing. Do you agree? If the absolute value of pi i's end up being 2, 3, 4, 10, 15, 20, when you sum, eventually it's going to go to infinity. But if that is a decreasing sequence of numbers, then when you sum it, it has to be less than infinity. That is a condition for the MA side. The same condition, but I'll be writing here, lie outside the unit circle, the AR2 model is causal. Same applies for the AR1 model as well. Good. So on this side, divide when you divide 1 over PZ on the MA side, we get the sine weights. So the sine weights must be less than infinity, or the sum of absolute value of sine weights must be less than infinity. This is what we call L1 convergence. There is L2 convergence, but no way to write it. This is good enough, you get the point. Yes, oh, we're clear. Okay, sorry, I mixed them up. So that is our polynomial phi or z, and I wrote the properties of that over there. Remember, we did this while we were doing second order difference equations, right? And I said, if we can understand the difference equations properly, later on when we get to AR models, MA models, things would be easier. So that's what our characteristic polynomial is. And there are 3 possibilities in terms of roots, right? What would be used to find the roots?
Quadratic.
The quadratic formula. So minus phi1 minus b plus or minus b squared minus 4 times a times c divided by 2n. Yes. So this is a, that is b, that is c, right? Minus b plus or minus b squared minus 4ac over 2a. A is negative 2. Good. So what is going to determine if we are going to have real roots or imaginary roots?
Whatever V2 is,
When we're what?
whatever V2 is, right?
Whatever phi 2 is.
Or it's whatever is under the square root if it's negative.
Right. So
So it has to be dependent on what V2 is, because V1 squared will always be positive.
still that is not correct. What if phi 2 is positive?
That is not a complex group.
Exactly. So you can't say whatever phi 2 is. The correct condition is that has to be less than 0. Yes? Do we agree? The roots are going to be distinct if that is not equal to 0, and whatever that you have is positive, then you would have plus or minus something, you would end up having 2 roots. The last case, the roots are repeating. When would that happen?
If that equals 0.
If that equals 0. Can I erase this side? I'll give you a minute to copy. Now, why are those important? So, that's what we have, which would mean that's correct. Which would mean that is our notation. Yes. And this part, if we find the coefficients, it's simply 0 to infinity, the psi weight multiplied by epsilon t minus k. We did this last time or the time before. How do we go from here to there? We find psi weight and we know there is a lag operator that is attached to each psi weight. So psi 1 would have a lag of 1, psi 2 would have a lag of 2. So as k goes from 0 to infinity, psi 0 is always 0, epsilon t minus 0, epsilon t. Psi 1 will result in a lag 1 on epsilon t, so epsilon t minus 1, and so forth. So this pretty much is what we call a filtering operation, or a linear filter.
You said it's going to linear filter.
Yeah. Good. So the psi values the absolute value of the psi values, when you sum, it's less than infinity, it's constant. Great. Now, what was the expression for this size?
To the J.
So here we'll have C1,
Yeah, that
lambda 1 raised J, C2,
one.
lambda 2 raised J.
I guess I should write that as a lambda.
Correct.
People see.
And that is only for an AR. If there is an AR 3 model, what would we have?
See.
Plus C3, lambda 3 raised J, and so forth. Now, lambda 1s relate to the roots over here of the characteristic equation. If the roots lie outside the unit circle, Z1 and Z2, lambda 1, lambda 2 would lie inside the unit circle. And as you increase the powers, it's going to decrease and go to 0. So we have the psi j expression for an AR2 model. Now, we have to pay attention to the roots, lambda 1 and lambda 2. So if the roots are distinct, then lambda 1 and lambda 2 are distinct. Do you agree? If the values Z1 and Z2 are different, then those two, they have to be different. So that would work. Good. If Z1 and Z2 are repeating, then lambda 1 and lambda 2 are repeating or are the same. Right? In that case, I can't write psi j if I simply did psi j as equal to C1 lambda 1 raised j, C2 lambda 2 raised j. They are one and the same, excuse me, one and the same. So lambda 1 equals lambda 2 equals say lambda. What would happen? You end up having C1 lambda raised j, C2 lambda raised j. Correct? We have lambda raised j in common, and we'd end up having C1 plus C2. But C1 plus C2 is a constant, right? So I can just call it C. We must have only one C. The reason being C1, C2 depend on lambda 1, lambda 2. If they are the same, then that's what we're going to end up getting. Not only that, the constant C depends on lambda 1 divided by lambda 2 minus lambda 1. So the denominator will become 0. So that doesn't work. Right? So if we go back to differential equations, Evan, did you take, oh, you did take,
Did, yeah.
okay.
What's the C plus?
So if you, no excuse, if you have repeating roots, the solution to a differential equation, we write it in a certain way. Do we remember?
Do we have like a T or something?
Or it's like G to the T minus something.
E raised 2 comes if the roots are complex. So when we have repeating roots, we can write psi j as C1 lambda 1 raised j plus C2 j times lambda 2 raised j minus 1. If you have more repeating roots, you write it as j squared lambda 3 raised j minus 2 and so forth. Good.
Can you, that doesn't work again, sorry, I was busy running.
Come again.
Can you repeat why that doesn't work again a little bit?
Well, 2 reasons. One, if do you follow this part?
Yeah.
So if the lambdas are the same, we have lambda raised j multiplied by c. So psi j cannot just depend on one lambda. We have 2 denotes AR2. That's the straightforward explanation. Mathematically, if you recall, C1 was lambda 1 over lambda 2, excuse me, lambda 1 minus lambda 2, right? If they are the same, what do you think would happen? They'll divide by 0. So, will not work, which is why we have this. In this case, sure, they can be the same. We can't combine directly because there is a chain of it. Good. Last case.
Then how would we find the C1 and C2 in this case? Because when the 1 and when the 2 still be,
It could come again.
how would we end up finding C1 and C2 in this case? Because when the 1 and when the 2 still.
We will do it when we get to a problem. So that's a good question. You know, if they are the same, how are we going to find C? We will get to that when we do a problem. So case number 3. If Z1 and Z2 are imaginary, then lambda 1 and lambda 2 are also imaginary. Do you agree? 1 over an imaginary number is still an imaginary number. So both of them are imaginary.
Wait, so for these other 2 cases, you're not adding lambda 1 and lambda 2, or is it just another way of writing and?
Which one?
It's not adding, it's an and sign.
It's not adding, okay.
Oh, that one's,
I know, I write my and signs like that too.
That's lambda 1 plus.
okay. So if Z1 and Z2 are imaginary, lambda 1, lambda 2 are also imaginary. So we don't want to write it as A plus BI, even though it would work. So let's say root Z1 is A plus IB, then what is the root Z2? A minus IB. Why? What
Yeah, the plus and minus.
Okay, but what if you had the cubic equation and you had an imaginary root? Huh?
Yeah.
we wouldn't use the quadratic formula. My question is here, your answer was, oh, it's because of the quadratic formula. I agree. It was very good. But was it? It was a cubic equation. And you got one imaginary root. What does it imply?
That we should panic.
What? You should panic. Aren't you like senior?
I'm already having a crisis.
I think that's everybody, that's junior high.
Complex roots always occur in conjugate paths, right? If there is a root that is a plus ib, the other root has to be a minus ib, right? So if you have a cubic equation and you had one complex root, that implies there is another complex root, which is the conjugate of this one, and the other one has to be real. Does that make sense? So conjugate, complex roots always occur in past. So sure, we can write it this way, but this causes certain problems. So some like to call it theta, some like to write it as omega, some write it as 2 pi f. It's a matter of choice. This is another way of representing a complex number. So it is in, all the form you have R and theta, Oilless formula. If that is for a plus ib, for a minus ib, what should we have? Good. So those are the two things. But we've got to know what R is. Well, R is the magnitude right, R is square root of a squared plus b squared. Now, if you did the complex plane of whatnot, it's a right angle triangle. You have a point A plus IB. So that is A, that is B. A squared plus B squared. So the distance would be square root. The length would be square root of A squared plus B squared.
So it's just C.
So cosine theta would simply be equal to adjacent over hypotenuse, so A over square root of A squared plus B squared, which is R. Sine theta would be equal to B over R. So tangent theta would be equal to B over A. Now you can find theta in any of the three ways using cosine, sine, or tangent. I'm going to use tangent. That's what I makes it theta. Tangent inverse of B over A. Right.
That's what it is so proud.
So we know how to get R, we know how to get theta. We sort of did this with a second order difference equation a long time ago. But how do we relate it to our psi j? So psi j in this case would be C1 lambda 1 raised j. So if Z1 is R e raised I theta, what is lambda 1?
1 over that.
1 over that. Yes. So that would give us C1 1 over R e raised I Rj e raised I theta j plus C2 1 over Rj e raised minus I theta j. Good. Mind you, I'm using the roots Z1 and Z2. Had I wrote 1 over lambda 1, excuse me, 1 over Z1, called it as lambda 1, express lambda 1 as A plus IB, lambda 2 as A minus IB, this R raised J would be in the numerator. Does that make sense? So what I'm trying to say is I'm using the actual roots, expressing them as complex numbers. But if I had inverted those, then that Rj will be in the numerator. Do you agree? Because it's 1 over lambda, which is 1 over Z1, so to move to the numerator. So good.
So this is the final.
So this is you
It-
expressing, you know, that. Now where do we go from here? There is the Oilless formula, which states I can write the exponential as cosine theta j minus I sine theta j. Yes. Correct. What do we have? Well, we have 1 over Rj in common, or R raised j. If I pull that out, I will have C1 cosine theta j minus I C1 sine theta multiplied by j. C2 cosine theta j plus I sine theta j multiplied by C2. Agreed. I just distributed the C1 and C2. Have common terms here for C1 and C2. C1 cosine theta j, C2 cosine theta j. So I will have C1 plus C2 cosine theta j. Yes. Likewise, I have C1 sine theta j, C2 sine theta j. So plus I, C2 minus C1 sine theta j. Good. Now, you may look at that and say, well, our psi j's are imaginary, correct? But if they are imaginary, all of our psi weights are imaginary, and we can't have that. So how do we go from here to just having real values? Because we need real values. Because if you go back and look at psi naught, psi 1, psi 2, in every single case, they were real numbers. We want real numbers, but unfortunately we have an imaginary number. So there is a way to get around this. We will do that next time. I don't want to start it now. But keep in mind, Z1 is A plus IB, Z2 is A minus IB. I'm using these two directly. Your book starts here with lambda 1 and lambda 2, right? It's doing 1 over. Because it is 1 over, here it will become RJ, and here the sign will just flip, right? The conjugate of that, right? Complex number conjugate. So it'll just flip and you get RJ, R raised J in the numerator. Good. That's a good place to stop. We'll pick it up from here next time.